Welcome to the fourth lesson on magnetism and electromagnetism. This lesson only covers higher tier content, so if you entered for the foundation paper, you don't need to use it. So we're going to look at the motor effect and something called Fleming's left-hand rule. So the lesson, you're going to need a pen, some paper and exercise book to record some answers and make notes if you need to. If you've got your mobile phone on, get it out of the way, get it on mute unless you need to actually watch this video on it. Keep your distractions to a... Okay, so straight onto the starter. I want you to look at that, which should be familiar from a previous lesson, and I want you to tell me from that diagram what can tell you about the magnetic field around a permanent magnet, a bar magnet. Okay, you've had 30 seconds. I might not run it for the full 2 minutes. I'll give you about a minute more. If you think you're finished, just check that you've got as much detail about that magnetic field as you can. Okay, I'm going to finish it off there. So you should see there you've got the plotting compasses, and remember that the plotting compasses are going to show a direction from north to south. So the magnetic field is coming out of the north and going into the south. So that means the red side of the bar magnet there must be a north pole. So the magnetic field is coming out of the north pole and going into the south pole. You should also see that round the edges of the bar magnet there, that it's curving round. You may have put that the magnetic field is strongest at the poles and it gets weaker on the sides and it gets weaker the further. Let's move on then. So the first outcome is we simply need to state the factors, state the things that are going to affect the size of the force that we have on a conductor. So if we have a conductor, something conducting electricity that's in a magnetic field, it'll have a force on it. So that's what we're going to explore. The other outcome is to use something called Fleming's left-hand rule to talk about direction. We will be doing some calculations in this lesson as well, and that'll be using a formula that's new to you, but it's a given formula. You don't need to memorize it for the exam. So we've seen before, diagram there of electromagnet, that around a magnetic field, around a current carrying wire, we can have a magnetic field. So there we've got turns, coils wrapped around a piece of soft iron, and it will give us a magnetic field. And the direction of that magnetic field is actually going to depend on which way the current is going. So there we've got the north pole on the left and the south pole on the right. So we know then that we can get magnetic fields from currents. So now we've got a wire, just a straight piece of wire this time, and not a coil connected to a cell. So we've got current flowing from the top, the positive side of that cell, round through the red wire and into the negative side. So we've got a wire, it's carrying a current. So then we know that that wire will make a magnetic field. So there'll be a magnetic field, quite a small one, but a magnetic field around that wire. So then, if we put that wire that's got a magnetic field around it and we put that next to a different magnet, what do you think will happen? Let's have a look at the force on a current carrying conductor. So what we've looked at previously is anything that's carrying electric current will have a magnetic field around it. So what we've got set up here, we've just got a wire that you can see, and that's carrying current. Now I've put a little bit of card there, it's showing you which way the current is going at the moment when I switch it on. So it's coming out the positive side of the power pack. It's going to the ammeter so it can show us how much current is flowing through the wire. And then out of the ammeter and along this wire in that direction, so the current is going in that direction. And then returning to the power pack. So that's the current. Now we know that when we put current through that wire, it's going to produce a magnetic field. Now, what we're going to look at is something called the motor effect. Motor meaning movement. So it's a movement caused by a conductor conducting electricity. So there's electrons moving through it in a magnetic field. So what we've also got now is another magnetic field. And you can just see there's some magnets here, magnets there. Now that big face of that magnet there is a north, and the one above it is a south. So we've got north and south. And if you can remember from before, the magnetic field goes from north to south. So the magnetic field inside there is just going up. So I've got that arrow there. So if you imagine the magnetic field is going up all the way inside there. So current in that direction, magnetic field up. So I'm going to switch it on. You'll see a value, 3 amps or something, will flow through there. I won't have long because it potentially will overheat. All I want you to do as I switch it on is to have a look at that wire, and we're looking for movement, motor effect, movement effect. So I want you to look. What's it do? Where's it go? Okay, just about 4 amps there. So pretty obvious. It started moving in that direction. Let's have another look. Yep, it's definitely going back in there. So the force then on that current carrying wire is in that direction, that way. Current that way, magnetic field that way, force that way. I'm going over it lots of times because you'll need to be able on a diagram in your exam to use these directions to work out what's going to happen. So what I'm going to do next, I'm just going to take that off, is I'm going to reverse the current. So instead of the current going that way, I'm going to reverse it to that way. So all I need to do is to swap that one with that one. Swapping the plus and the minus, the positive and the negative terminals round. So now what we've got the current going in that direction. I've not changed the magnetic field, still north to south, so it's still going up. Switch it on, let's have a look again. You've probably worked out what's going to happen. Bit stuck there. Moving the way, not very convincing. Let's just give it a blast, turning it up. Okay, definitely coming out towards the camera. Out, out. That's better. Right, so this time the force was out. So we've reversed the current and we've reversed the force. Okay, what I'm going to do now, take that off, I'm going to leave the current as it is. This time I'm going to just swap the magnets around so that the north pole, pretty strong magnet, is at the top and the south pole is on the bottom. So I need to swap that round. So this time the magnetic field is down. So current that way, magnetic field that way. Let's switch it on. Oh, and it's reversed again. So it's reversed. So reversing the current reverses the force, and reversing the magnetic field reverses the force. Now I'm not going to swap both again, because if you swap both you'll end up back where you are. Makes sense. So in summary then, the force on a current carrying conductor needs, to get that force, you need a current flowing and you need a magnetic field somewhere around the wire. So the force depends on the current
and it depends on the strength of the magnetic field. So we'll come to an equation later on with that, and we'll look at how we can use the motor effect for a motor, which is where motor gets its name from.
More dramatic version of the same thing, just using much higher currents from that car battery. Force up. There's the current. Force down. Okay, so we've got a diagram now that looks more like the type of diagram that you might see in an exam question. So we're going to look at the force on the current. Now we're going to use the letter F for force, so that's going to be something that we would measure in newtons because it's a force. So when we've got a conductor, so that could be a piece of wire, carrying a current, and we put that in a magnetic field, we're going to get a force. So there'll be a force between those two, because really they're both magnets. We call this force the motor effect. So the word motor means movement, so it's a movement effect. Now, if you've got a couple of heavy magnets and your wire is lighter and your wire can move or bend, we've seen that that wire will move because the force is on it. Now this is new. You'll only meet it for a couple of lessons, and then apart from in your exam you may well never meet it again. So we've got something called the magnetic flux density. Well, we use the word density because we're thinking about the magnetic field in terms of the lines that we represent it with that we've used already. So if the magnetic flux is dense, it means the lines are close together. So if we've got a high magnetic flux density, it just means it's a stronger magnetic field than if it's a lower magnetic flux density. Now we use the letter B here. Don't worry too much. If you need to use this in a formula, that symbol will be there and it's on the formula sheet. So no panic about that. So flux is another word for the field, and we know it runs from north to south. The closer the lines are together, the stronger that field is. Large flux density on that one. Small flux density on that one. You've probably heard the word Tesla before, car manufacturer, electric car manufacturer. So we measure the magnetic flux density in Teslas. So if we had a magnetic field that had a flux density of 15 Teslas, that would be how strong it was. And 15 Teslas is a very strong magnetic field. You're more likely to get magnetic fields 0.1 or even less Tesla.
So we understand the motor effect, and we know that if you've got a current in a wire and that wire's in a magnetic field, we'll get a force. But now on the higher paper, we need to talk about how you calculate the value of that force. So I'm going to introduce this equation to you. It's a given equation, so it's on the formula sheet on paper 2. Force, so that's newtons, equals the magnetic flux density, and the symbol for that is actually B, but I'll put these in symbols in a minute, and we'll measure that in Tesla, so that's the strength of the magnetic field in there. That times the current, and current's in amps, and that's times the length of the wire, and that's meters. So it's the length of the wire, not all of it, it's just the length of the wire that's in the magnetic field, so it's just going to be that bit there. So F equals B times I times L. F equals Bill. It's quite easy to remember, but it's a given formula, so you don't need to. So we'll apply our setup here to that equation and then work out a value for the force on that wire. So we're going to find F. So we're going to need B, we're going to need I, and we're going to need L. So B, you're not going to know unless you're told. So I'm telling you that B is 0.1 Tesla. So that's the magnetic flux density, the strength of that magnetic field in between those magnets, 0.1 Tesla. 1 Tesla is actually a pretty strong magnetic field. The current, we'll know when we switch it on. We're going to read it from there. The length of the wire, well, we can measure it. It's just that bit, 5 centimetres. Need to be careful. It's got to be in metres, so I'm going to write that straight away. 5 divided by 100, because there's 100 centimetres in a metre. 5 divided by 100 is 0.05 metres. So we know the magnetic flux density, we know the length. So we'll switch it on and we'll get a value for the current and we'll see the force. So let's switch it on. Now it pops the wire. 5 point. It's pretty much hitting 6. So let's call it 6.00 amps. So we've got everything we need now to find the amount of force. So the force equals B, magnetic flux density, that's 0.1, times 6 amps, times 0.05 meters. So you pop that into your calculator. I'll let that do it yourself while I find my calculator. So 0.1 times 6 times 0.05, which gives me a force of 0.03 newtons. It's not a big force. You can see that it's not a particularly big force. We're just getting that little bit of movement, easily stopped. It's not a big force. I just about feel it when I touch it. So this equation means then, if we were to increase any one of those 3 things, we'd get a bigger force. So let's just see it. We're not going to do the calculation again. Let's just see if we can visually see that effect. So the easiest thing for me to turn up is the current that flows. So if I turn up the potential difference, the voltage on the power packet, it'll give me more current. So we'll flick it on and we'll see that that value is bigger. And we should see that this force is looking stronger than it was before. Okay, so that's 10 amps. That's actually quite a lot of current. It's going to get hot. So let's ramp it up again, see how far we can do it and get away with it. Definitely looking stronger. That's 14 amps. And again. Right, that was the fuse popping out. So that's probably as far as I'm going to go. But increasing the current is going to increase that force. What I could also do to increase the force on the current carrying conductor is to increase the strength of these magnets. Now I could replace them and get stronger magnets. That's one way that I could do it. Or if these were closer together, which I can't do without them actually sticking, if they were closer together, that would make the flux density possibly a little bit more concentrated in a smaller gap there. So you can see that that's been done already, which is why there's 2 pairs on there. So I could do that, or I could increase the length of the wire. Now increasing the length of the wire in there is quite difficult, but when we come to looking at motors towards the end of the lesson, you'll see that in a motor we don't just have one piece of wire to get a force. We have it going round and round and round, and all the coilers that you'll see later is an attempt to get a much longer piece of wire in that magnetic field, and the longer the piece of wire, the greater the force. So the greater turn that you can get on your motor.
So now we're going to have a look at how we calculate this force. We've got the equation. Force equals magnetic flux density times current times length. F equals BIL. F equals Bill. I find it a little bit of a shame that that's given in the formula, because actually it's quite a straightforward equation to remember if you just remember it as F equals Bill. So the force is newtons, the magnetic flux density we measure in Tesla, the current in amps, and the length in meters. Because this formula is only on the higher questions, on the higher paper, you'll also tend to find that they might give you numbers in milliamps or numbers in millitesla or millimeters for your length. So be aware that there might be some conversions in these questions, and it might make the question worth 4 or even 5 marks in the exam. So let's have a go at a work example. If you want to record this in your book, it's probably a good idea, and it might help you do the questions that are going to follow. So find the force on a wire of length 5 centimeters. There you go. You should notice that straight away. 5 centimeters, it's going to need converting. In a magnetic field with a strength of 0.1 Tesla. The current through the wire is 6.0 amps. Got 5 centimeters, that's the length. 0.1 Tesla, that's B, the magnetic flux density, and the current is 6 amps. So I've written them down the side, that's good practice, and as I've done it, I've converted the length into meters straight away. So 5 centimeters, there's 100 centimeters in a meter, so you divide it by 100. It's 100 times smaller when we put it into meters. So now all we need to do is just to substitute into that formula. So the force is 0.1 times 6 times 0.5, so we get 0.03, and because that's a force, we've got newtons. Now that question there would be worth 1 for the conversion, 1 for the substitution, 1 for the answer of 0.03, and if you needed to put n in your answer and it wasn't there, there'd be 1 more for that. So that's a 4-mark question, and really it's a simple substitution. If you forgot to convert your centimeters to meters, you just lose the 1 mark there. So we're going to do 4 quick fire calculations here. I'm only going to give you 30 seconds each, so I'm going to try and get you to do them pretty quick. Don't panic if it's taking you longer, just pause the video. So first one, calculate the force produced when, let's go. Okay, this will be a 3-mark question. There's no conversions, so you'll get 1.5 newtons. If you put 1.5 N, just be careful that you've put a capital N, because the proper symbol is a capital N, and all the symbols that are surnames are capital letters. So 1.5 newtons. Question 2, 30 seconds. Again, this one will be a 3-marker. Okay, 15 newtons. 15, capital N. Off you go. Careful, conversion in this one. It's worth 4 marks. Nine newtons then. 2 conversions in this one. This would be a bit unusual, but it's going to make it worth 5 marks. just before I pop the answer up. So that 25 millimeters needs dividing by 1,000 to put it into meters, and the 200 milliamps needs dividing by 1,000. If your answer looks similar, but it's 1,000 or 1,000,000 times out, that'll be why. So 0.0025 newtons. Right, so let's introduce Fleming's left-hand rule then. A lot of students get a bit het up about this because it can be a little bit difficult. Not so much remembering Fleming's left-hand rule, but doing it with three-dimensional diagrams in the exam. Generally, it's only going to get you 1 mark, so no panic. But you use your left hand. You put your fingers out like you can see on that diagram. Now the force is going to be represented by your thumb. So that's going to give you your movement on your wire when it moves. So force is up in that diagram in the same direction as the thumb. The first finger is going to be the magnetic field, first finger field. So that's going to point, the blue arrow would be from north to south. You'd need to point it along the north-south direction. And then you've got the current, second finger is your current. And then that's the way that it'll be. All the three of them are at 90 degrees.
Let's move on to Fleming's left-hand rule then. So Fleming's left-hand rule. Now, all this will allow you to do is to be able, from a diagram, to work out which direction the force is. So don't get bogged down by this. It can be slightly confusing. Not confusing because it's difficult to remember or difficult to use. When you're in the exam, you're going to have a diagram that represents 3 dimensions, and it's sometimes that causes the problem. So let's first of all make sure that we can explain how we use Fleming's left-hand rule, because that could be a question within itself. So this may seem really obvious, and apologies if it is too obvious, but please use your left hand. If you use your right hand, you will get the wrong answer. So we've got our left hand. Now, the reason that your left hand can be useful is because we can use 3 fingers to represent 3 things that we've got. And by holding our thumb at 90 degrees to our first finger and your first finger at 90 degrees to your second finger, you can use this to work out the direction of the force. So your thumb is going to represent the motion of the wire. So if you think of or motion of the wire, so your thumb is going to tell you which way this wire moves. Then your first finger is going to give you the direction of the field from north to south. So here it's straight up, so the first finger is going to be pointing straight up. First finger field, which leaves your second finger is going to represent your current, the direction that the current is flowing in. So at the moment the current is flowing in that direction. So thumb, motion, second finger is the current, and I missed out the first finger is the field. Thumb motion, or your force, first finger field, second finger current. Right, so let's apply it to this situation. We've got the current in that direction, so which one's the current? That's the current. So the current is in that direction, so I'm pointing my finger in that direction. You will look a bit of a fool in the exam, by the way, but there you go. So second finger current, first finger field. So I've got to manage to get that finger pointing that way and that finger pointing up. So the only way I can do it is to hold it like that. Field's pointing up, north to south. Second finger's pointing that way, which means my thumb now is pointing out towards the camera. So the motion, the force on this wire should be out towards you. So let's switch it on. There we go, yes. So let's change one of those round. Let's take that off. It's easier for me to leave the field where it is. Let's change the current round. So remember to change the current. I just reversed the polarity there. So now the current is going from positive to negative. So it's going that way. And we should remember what happens when you swap them over. When you swap them over, it just goes the opposite way. So it's going to go in this time. So the force is going to be that way. So let's check it with Fleming's left-hand rule. thumb is going to give us the motion. First finger is going to give us the field. Now I didn't change it, so it's straight up. But this time the current isn't that way, it's that way. So the current is that way, the field is up, and this time my thumb is pointed away from you, so the force is going to push it that way, away from you. So that's Fleming's left-hand rule. It'll take a bit of practice. Generally, if you're using it in an exam to find the direction of the force, it's only going to be 1 mark, so it's nowhere near as important as being able to use the equation that we've just done. The minimum you must be able to do, though, is to be able to explain how you use your left hand to help. So when you're doing that question, you're talking about your thumb showing you the motion of the force, your first finger being the direction of the field, and the second finger being the direction of the current.
Okay, so here we've got a left hand. Just a reminder, please use your left hand. We've got a magnetic field that's going from north to south. So the first finger in that diagram is pointing from north to south. The current is coming sort of out of the page there, which will give a direction of the force up. So that current carrying wire would be forced up. So the magnetic field there, remember, is always going from north to south. Then if we put a wire in there, so that wire, let's put a current that way. And what I want you to do is to tell me which way the force would be on that wire. So first finger field, north to south. Second finger current, which way is the force on the wire? Okay, I'll just give you 10 seconds. Okay, so it would be up. Right, you have a go. So what I want you to do then, north to south, that's the way the current is. Use Fleming's left-hand rule. Use your left hand to work out which way the force will be on the purple wire now. Okay, if you've been a bit clever, you'll notice that the field is just going the opposite way from the one we did before, which will mean that the force is going the opposite way. So the force is going down on that. Okay, try that one. And it ends up pointing that way. Another one. This time it's going that way. So I'm going to give you 4 minutes now to have another go at the calculation questions. So question 1 there is finding the force. And question 2 is finding the force. Just be careful that all your units are right. Take your time. If you have a bit of time at the end, explain how you can find the direction of the force. So the stretch question there is really explaining how you would use Fleming's left-hand rule. Because it's 3 marks, you're talking about what your thumb represents, your first finger represents, and your second finger represents. I have missed off the amount of marks that question 1's worth. It's worth 3. Okay, should be on question 2 or even a bit further. Just a minute left. Quickly onto the stretch question if you get time. Right, let's see how you got on. So the first question, there's no conversions, it's just a straightforward substitution, which should give you to 3 significant figures, 0.375 newtons. Second question, extra mark in that question because it's given you the length in 60 centimetres. So 60 centimetres converted into metres, so that's less than 1 metre. It's 60 divided by 100 because there's 100 centimetres in a metre, which gives you 0.6. So 0.6 times 1.5 times 0.6 is going to give you 5.4 times 10 to the minus 2 newtons. So the stretch question, for your marks, you need to be saying that you use your left hand. You need to say that the thumb is going to represent the movement or the force on the current carrying wire. Your first finger is going to represent the current. Sorry, wrong. Your first finger is going to represent the field, and your second finger is going to represent the direction of the current. It might be worth saying that you hold the 3 of those at 90 degrees to each other. So, got 6 questions here worth different numbers of points, A, B, C, D, E, F. Generally getting more difficult as you go down. So what I want you to do, I don't expect you to do all of them because it's going to take you about 15 minutes, but if your sort of target's a grade 5, just perhaps do the first couple. If your target's a higher, a 7 or 8 or a 9, just do the last couple. I'm going to put a couple of minutes into the video. If you need more time, then just pause it, or if you do feel that you'd like to do all of them as a bit of a check, then pause the video until you've finished and then move on. So I'm just going to time 2 minutes, pick what you're doing, and then we'll have a look at the answers. Okay, so if you need more time to do your 2 questions, or you just need more time because you'd like to do more questions, pause it now before I move on to the answers. Okay, so let's just have a look at A, B, C, D, and then we'll have a look at the others separately. So question A, that's your F equals BIL. Remember, that is a given equation on the formula sheet, so really you just need to recognise it and know what everything's measured in. So B, 0.2 Tesla. C, 1.6 Tesla. Sorry, 1.6 newtons, because it's a force. And the last one, 0.13 Tesla. If you've got any of those calculation questions wrong, what I suggest you do is to go back in the video to where we've modelled it through before on some of the more simple questions. Have a go and then come back. Last couple. We've got some conversions there. So millitesla needs converting to Tesla. Remember that there's 1,000 millitesla in a Tesla. So 2,000 millitesla is the same as 2 Tesla. So that should give a force of 1.8 newtons. And then the last one, you've got a conversion of millimeters. So 500 millimeters, that's half a meter, it's 0.5 meters. Should give you an answer of 120 amps. Okay, if you complete the Google quiz now, that'll be automatically marked and you'll get your feedback pretty much straight away. And then if you'd like to record a lesson summary in there, we've got a couple of sentences on the motor effect, a calculation that you could add as a summary there for F equals BIL, picture of Fleming's left-hand rule, what represents what, and then just an example of how you can use Fleming's left-hand rule to work out the force on a current carrying conductor. So the next video is going to be a shorter video where we're just going to look at electric motors.